interviewing Dr. Luke Barnes about his recent research exploring multiverse predictions for what's generally regarded as the most finely tuned parameter, the cosmological constant. His blog reveals at least 23 recent popular level articles that have referenced his research. So it's getting a lot of attention, as it suggests the multiverse is not as good of an explanation for fine-tuning as was previously thought. In this video, Barnes provides background information about this important constant and discusses expectations prior to his research for its level of fine-tuning, also explaining about a theoretical possibility that might minimize the fine-tuning. Dr. Barnes is a postdoc researcher at Western Sydney University, has a PhD in astronomy from the University of Cambridge, and he's published several papers in the field of galaxy formation and the fine-tuning of the universe for life. He authored with Geraint Lewis A Fortunate Universe, Life in a Finely Tuned Cosmos, published by Cambridge University Press, which I think is the best book on fine-tuning. Dr. Barnes also published papers on the philosophy of science and regularly engages in public outreach. I highly recommend his blogs at Letters to Nature, and many of them deal with fine-tuning. I first asked Luke to explain the background for lambda, the cosmological constant, and why it's received a lot of attention within the physics community.
So lambda has a sort of interesting checkered history. At one point, Einstein called it the greatest blunder of his career. So that, to be able to come back from Einstein, writing you off is an interesting thing for a parameter to do. When Einstein first derived general relativity, he was looking at, how do I describe gravity? And he had this idea that it's the geometry of space-time. To get from his ideas towards the final equation that his theory was in, he sort of took the straightest path. He just took the simplest things along the way. Of course he did, because that's what you do. When he got there, another physicist, Alexander Friedman, showed that if Einstein's theories were true, then the universe as a whole can't be stable. It can't just all sit there. It's either got to be expanding or contracting. Something's got to move because gravity is always pulling in. And Einstein thought that this was abominable. So what he did was put in an extra constant into his theory. That he sort of reversed back up and took, instead of the simplest path, just took the first complication he could, which was to add this extra constant into his theory. Having done that, you can make a universe which is static, in which the attractive pull of gravity is sort of opposed by this cosmological constant, this number he puts in, which opposes that, and then you have a stable universe. It was shown shortly afterwards that that universe is static in the sense that a pencil sort of balanced on its end is static. The slightest push will turn it one way or the other.
Sure.
So Einstein then discards the cosmological constant. It doesn't do what he wants to do anyway, so it can go. But it's still there kind of in the equations. It's still, something that could follow from his principles. And so it sort of hangs around the fringes of physics for many decades. The real blunder for Einstein was not so much that he introduced a constant, but that he should have just believed his theory when it said the universe had to be expanding or contracting, because then he could have predicted the expansion of the universe, or at least expansion or contraction. But then, so the cosmological constant goes away and comes back a couple of times. People think we might need it, and then it goes away, sometimes 50s and 60s. Starting in the early 90s, there are suspicions that we need it back again for various reasons. There are good reasons to think that the universe as a whole has a certain amount of energy density in it, what's called, gives it a flat geometry is what it's known as, but there's not enough matter to do that, so we need something else. So maybe it's the cosmological constant. The universe seemed to be a bit too young for some of the stars in it. If you took the expansion of the universe and went back in time to a beginning, you got about 9 or 10 billion years. But we were finding stars that we thought were about 13, 14 billion years old. So that's a bit of a worry. And so for these, there are a couple of other reasons as well. We thought we might need the cosmological constant back soon. But the real crucial discovery was in 1998, when they mapped out they measured the expansion of the universe in a very precise way. And in particular, they could tell whether the expansion was speeding up or slowing down. So the expansion of the universe means go find a galaxy over there. It's moving away from us, right? And the further away it is, the faster it's moving away. That's the expansion of the universe. We've known about that since the 20s really. What we discovered in 1998 was not only is that galaxy moving away from us, it's moving away faster today than it was yesterday. And if you want that, ordinary matter won't do that, but a cosmological constant will. And so that's where the cosmological constant comes sort of roaring back into cosmology. So it's been back since 1998. So the question then is, why it's sort of interesting to fine tuning, is we want to know what sort of thing could this be? In particular, is it a sort of pure mathematical constant, the way Einstein did it, or is it some form of energy in the universe which has the same sort of effect? That would generically be called dark energy. And one of the candidates for that, which seem to be there in physics as we know it, is something called vacuum energy. So all the stuff we see around us in fundamental particle physics, it's a bit of a misnomer. Particles aren't actually fundamental. Fields are fundamental. This sort of like a magnetic field, something that's everywhere. And then when a field ripples in a certain way, that looks like a particle. So you make particles out of fields. But when there's no particles there, you've still got the field. And here's what was discovered. If there's energy in the field, it will behave like a cosmological constant. The reason it's constant is you know, very roughly, heuristically, if the universe expands, there's still the field there and still there's the same amount of energy there, which is how the cosmological constant behaves.
And so that field is of very, very significantly stronger than the observed value of the dark energy or the lambda, the cosmological constant. Is that?
Yeah. So you sit down with the equations and you try to say how much energy is there roughly when I take all the particles away, how much is just in the field, and you get an enormous number. So on a scale in which the amount in our universe is 1, the sort of typical value you might expect is 10 to the power of 120. So a number with 120 digits. And so what happens if we just sort of picked one of those at random? Well, almost certainly you just sort of ruin the universe. It expands too fast for anything to stick to anything else.
Right. Now, sometimes the numbers quoted are a bit smaller than that, 10 to the 60th or 10 to the 53rd. Is that related to supersymmetry?
Yeah. So as we looked around for, you know, why we have a small cosmological constant, there's this idea from particle physics called supersymmetry. So let me try to explain that. It's a bit strange. There are roughly two types of particles in the universe. Okay? There are ones that are called fermions. There are ones that are called bosons, and there's various things that distinguish the two. For example, light, the photon, is a boson, and the electron is a fermion. Now, there's various differences between them. It has to do with the way that they spin, but spinning is a weird quantum mechanical thing anyway. The important thing for our purposes is there's a theory that says at high enough energy, if there was lots of energy around, every particle would have a mirror particle on the other side. So for every fermion, there would be a boson with roughly the same properties, and for every boson, there would be a fermion with the same properties. So the way you name them is, if you have an electron, you put an S in front of it and call it a selectron. So that's the boson version. If that's true, then one of the ways that then for each field, its other field will sort of cancel out its vacuum energy above the range where when they're acting perfectly symmetrically. The problem is that we don't know whether supersymmetry is true, and even if it is, it only cancels things out above a certain energy level.
Right.
Okay, where you've got enough energy that you can make an electron and a selectron, and they don't care about how much energy is around. That energy is still so high that on a scale in which the cosmological constant is 1, that energy is 10 to the power of 50 or 60, probably closer to 60. And we don't even know if supersymmetry is true. So we've still got a problem of that magnitude.